Okay, what's up, everybody? Welcome back to another fun day of proof set theory and logic. How y'all doing? Pretty good? Yeah? Okay. So remember, we do have a homework this Friday. We didn't have one last week or did we have one last week? Maybe? No? Okay, we have one coming up soon. Homework 3. It'll be fun. It's a longer assignment. Helps you get in the whole proof writing mode, deal with sets a little bit. I'm sorry that it's long, but it's better to have a lot of proof writing about simple stuff to get ready to write proofs about more complicated things than trying to have you get more practice with the complicated stuff. Just like anything else, there's no way to get good at math other than practicing a lot, right? It's the same as piano or guitar or basketball or whatever. And you don't start trying to get good at basketball by doing super fancy, crazy moves. You just practice free throws, right? You don't try to get good at guitar by, like shredding out 6 solos right away. You practice scales. Same thing with proofs. So we're going to start out with like lots and lots of easy proofs to get used to it. And then we'll move to the more complicated stuff, and it'll be fun. So start the assignment if you haven't already. It will be no fun if you leave it for the night before. Whether or not it is fun, depending on, starting it earlier is anyone's guess, but it certainly will be no fun leaving it to the night before. So, cool? Yeah? Right on? Okay, so if you recall last time, the setup was, let me grab a better marker, maybe slightly better. That's much better. So the setup last time, we were defining the rational numbers by taking the set f, which we're defining to be the integers cross the naturals, and looking at the equivalence classes of f under the relation defined by AB is related to CD. I'll even say if and only if. What we said is AD is equal to BC. The notation is we write A over B to denote the ordered pair AB. So do you remember this setup from last time, how we were getting going? Yeah? We said, okay, let's look at ordered pairs. The first thing will be an integer. The second thing will be a natural number. Remember, under our convention, 0 is not a natural number. We start at 1. So the reason to do this is 1, because we don't need all the integers. If you have a negative on top and a negative on the bottom, then it might as well, just have positives on top and bottom, right? You can get the same stuff. And 2, this gets rid of the annoying problem of having zeros in denominators. Okay, we could totally do this with z cross z and then remove all of the ones that have a 0 in the second slot. We could do something like that. That's perfectly reasonable. But we're just going to go with this construction since it's a little bit more convenient to get started with. Okay, so we showed a few things last time. So we got this notation. Okay. Last time, we showed that this relation is an equivalence relation on F. This lets us talk about equivalence classes. So, what are the equivalence classes? Quick question for you, just to warm up and make sure we're getting everything that's going on. What are the equivalence classes? So under that relation, what are the equivalence classes in F? Well, the answer's not too bad. So the equivalence class of A over B, well, this is just the set of all C over D in F such that C over D, or I'll write it this way, A over B, it's an equivalence relation, so it doesn't matter which one we do first, but just to be clean about it, such that A over B is related to C over D. What does this mean? This is just the set of all C over D in F such that A D equals B C. Exactly like what that relation means. Yeah? Okay. So, if you just think about it, if AD equals BC, then regular old algebra says that, hey, what this is capturing is that A over C equals B over, or sorry, I'm writing this backwards. A over B equals C over D, right? But it's just a way to express that without having to, appeal to fractions, right? If we tried to define which fractions are the same by saying, well, it's the ones where the fractions are the same, that'd be a little bit circular. So we're going to use something simpler, like multiplication, to describe when fractions are the same. It's an equivalent way of writing it, but it doesn't use fractions. Okay, cool. So the equivalence classes are all the equivalent representatives of a given fraction. So, for example, what is the equivalence class of 1/2? That is the ordered pair 1, 2. Should be the set of all C's over D's in F such that, now our A is 1 and our B is 2, such that 1D equals 2C. Or another way to write this, just to make it a little bit cleaner, would be C over D in the field, or not in the field, in F, to be clear, such that D equals 2C. Or if you wanted to be even clearer about it, what would this be? You could even write this, if you wanted to be super clean about it, you could just say, hey, if D is equal to 2C, then I could just get rid of all of this stuff, right? And I could just say, all right, so if D is going to be equal to 2C, D lives in the naturals, C lives in the integers, you might as well just write everything in terms of C. So C over 2C such that C is in the naturals. Yeah? This is exactly what you would expect and hope to see in the equivalence class of 1/2. Stuff like, well, 1 over 2, 2 over 4, 3 over 6, and so on, right? Okay. So the equivalence classes do indeed capture your intuitive sense of, hey, there's a bunch of different ways to write the same number with fractions, right? We can talk about all of them at once by referencing equivalence classes instead of all of these distinct representatives of each possible equivalence class. Yes, question?
Where did you get the C as an element of the natural numbers?
So F, if you recall, F is Z cross N. So if C over D is in F, remember that our notation, this is telling us that C comma D, oh wait, I've said it, yeah, maybe I've said it backwards. No, this is fine. Oh, it shouldn't be in N, it should be in Z. Thank you, I think you've pointed something good out. CD is in Z cross N. Okay, getting ahead of myself now. But I have to be careful now. So if C over D is in there, I should be careful since if our equation here says D is equal to 2C, then perhaps I should, when I write that, I should say Z, perhaps what I should do is I should say C is in Z and then set minus 0. That would be the correct statement. Good, good. Okay, that's fine. Yeah? All right, right on. So this would also contain things like -1 over -2, stuff like that. Good. Yeah, that was a full-on mistake on my part. Thank you. writing too carefully, or not carefully enough. Okay, good point. Yes, okay. Anyways, yes, so it captures our intuitive idea that the equivalence class of 1/2 should be the set containing certainly 1/2, but also -1 over -2, and stuff like 2 over 4, certainly -2 over -4, 3 over 6, certainly like -3 over -6, and on and on and on, in either direction, all of the possible fractions that are equal to 1/2, with, whole numbers on top and bottom. Cool? All right. Kind of nice. So, here's our next question for ourselves. Question. Can we define addition and multiplication on the equivalence classes of f under the equivalence relation that we've defined? If I can write a tilde nicely. So can we define addition and multiplication? After all, we know we can define addition and multiplication of fractions, but now we have a different thing. We don't have fractions. We have sets of equivalence classes of fractions, which really are just ordered pairs, right? So can we define an addition and multiplication on these sets of equivalence classes? What does your intuition tell you? Does it tell you anything? No? Yes? Okay, maybe it doesn't. If it doesn't, that's okay. That's what we're here to do, is build this kind of intuition up. So, here's the idea. That is, since we have addition and multiplication on both n and z, certainly we inherit addition and multiplication on f by just, and now maybe I'm going to make a statement that is going to seem wrong at first, by just carrying it over. I.e., AB plus CD equals, and this is not right in terms of fractions, but I'm just trying to point out that you can do this, certainly. A plus C, B plus D. It's not quite what we want, right? And you could also take AB times CD and get back, say, AC and BD. Now, this won't be quite what we want, but I'm just trying to point out that anytime you have addition or multiplication on the components in a product, each of the sets in the component, like, if you have a set C that's A cross B, and you have an addition in A and you have an addition in B, you can get an addition in C just by doing it term-wise, right? Totally reasonable. As long as you have a way to add each chunk, then you can add pairs of chunks. Just do both of the additions at once. Okay, so can we do something similar to equivalence classes? That is, now this isn't quite how it works. For fractions, since A over B plus C over D is equal to, well, what? AD plus BC over BD, right? Okay. But can we carry this operation over to equivalence classes as well? Can we carry over any operation on F to its equivalence classes? So maybe this is a little drawn out, trying to point out what's going on, saying like, hey, can you bring any operation over to equivalence classes? But what I'm trying to do is give you some sense of like why we're about to prove what we're going to prove. That is, this might feel really unmotivated without thinking about this first. So when we carry an operation over to equivalence classes, what do we really need to have happen? It might feel like you can just do it willy-nilly, but the kind of potential big stumbling block is relatively obvious once you write it out. So the potential stumbling block is that the sum of two representative elements of two equivalence classes may yield an equivalence class that depends on this choice you make for the representative elements. So maybe kind of like say it more specifically. Here's kind of the way I would say it. That is, if x is in the equivalence class of A and y is in the equivalence class of B, then we can certainly define x plus y, or I'll write it this way, the equivalence class of A plus the equivalence class of B to be equal to the equivalence class of A plus B, right? But the equivalence class of x plus y may not be equal to the equivalence class of A plus B if x is not equal to A and y is not equal to B. That is, we could try doing this definition of it. We could say, hey, you can add two equivalence classes together by just adding together a representative element, but you may get different things. That is, you may have the equivalence class of x equals the equivalence class of A, and the equivalence class of y equals the equivalence class of B, but it could be the case that the equivalence class of A plus B is not equal to the equivalence class of x plus y. Does that make sense? It could be the case that which equivalence class you get back depends on your choice of representative elements for each equivalence class. That is, if you're trying to define an addition on the equivalence classes of a set under some relation, the problem that comes up is that if you're just using the addition that you have on the original set without the equivalence classes, like without the relation, right? It may be the case that things that get collapsed into the same slice of your set do not get mapped, do not have their sum mapped to the same things. Does that make sense? This maybe gives some sense of why our naive idea of just taking the sum like this, term by term, doesn't really work, right? That is, it's entirely possible to have distinct elements in each of these guys' equivalence classes produce totally different equivalence classes in terms of their sums. This is why we do this weird AD plus BC over BD business. That's, if you want to think of it like that, that's why we choose our addition of fractions to work this way. And maybe an easier way of thinking about why we choose our addition of fractions to work this way is because it, works out with your natural intuition of how ratios work. It is how things around you in the world work. But from a more abstract perspective, if you were, some disembodied mind floating in the void and you were just trying to figure out a way to do this, this would be a very natural way to come up with. That is, what do you need for this to happen? So, on F, we would need our addition to be such that AB plus CD equals XY plus ZW or maybe I should say this way, such that these equivalence classes are the same whenever AB is related to XY and CD is related to ZW. Does that make sense? See what I'm saying? You would want the sum of thing 1 plus thing 2 to be the same as the sum of thing 3 plus thing 4 whenever 1 and 3 are in the same equivalence class and 2 and 4 are in the same equivalence class. Yeah? So what does this mean? Well, that is, when are these guys related? I'll write it now in fractions. A over B is the same as X over Y, and C over D is the same as Z over W, then AY is equal to XB, and CW is equal to ZD. Yeah? Okay. So we're looking very similar to kind of what's going on here, right? Seeing some sums of products and stuff, right? Okay. So what we want now is for the sum of these things to also satisfy that. Does that make sense? So if we use our definition of the sum that we commonly encounter for fractions, that is finding a common denominator first instead of this bad definition, what we'll get is that this happens. So I'll prove that. We'll show that indeed you can define addition and also multiplication, though that one happens to be easier, but you can define addition on equivalence classes of fractions just by picking any representative element from each equivalence class and adding them together in the usual way by finding a common denominator. And that this defines an addition on an entire equivalence class, since the addition of any two representative elements yields the same equivalence class. How are we feeling about this? This is like one of those concepts where once it kind of sinks in, or once it clicks, you're like, oh yeah, sure, okay. But until it does, it feels like it's a bunch of, I don't know, mumbo jumbo or something, right? Any questions so far? Okay, cool. Basically, the picture So we will show, they'll draw a picture. So we'll show that the regular addition of fractions yields this compatibility. But the picture, if you want it in your head, is basically the following. So you've got your, let's call it, don't even think about ordered pairs for a minute. You've just got some sort of a set, big A, and you've got some kind of an equivalence relation on it. Remember what this does is this like cuts it into like lots of different slices, and each of these slices is an equivalence class, yeah? The idea is that if you pick something from one equivalence class and something from another, and you have a way of putting them together, well, that's just going to give you something in a different equivalence class. Now, if I pick two other things, one from each equivalence class, what we want to show doesn't happen is that it's not the case that you end up somewhere like up in a different equivalence class when you add them. That is, we want to make sure that this here does not occur. What we instead want to occur is we want our set to be all split into a bunch of different like chunks with our equivalence relation, try to draw the chunks about the same, and have it so that if you take a thing from each chunk and you add it together and you get a new thing, then any other ones you pick, they don't have to land you at exactly the same spot. They have to land you in the same chunk. So if you pick, say, like another one from A, or from this equivalence class and another one from here, then maybe they land you somewhere else when you put them together, but they always belong to the same chunk. Does that make sense? And the thing that can go wrong is having elements in the same chunks get put together to give you things in different chunks. That is, this black dot and that red dot are not in the same chunk, right? Well, here they are. So you want to make sure that that doesn't happen, right? We want to make sure they always end up in the same chunk. Cool? Uncool? Bad? Good, good. Thumbs up. I love this. Okay, good. So let's prove the thing we need. Now, what is this thing we need? Well, it's actually kind of straightforward once you just kind of write down this condition and you say, what do I actually want to show? And it kind of falls out right away. What it says is that, hey, if I have things that are equivalent, then I want their sums to be equivalent. Or pairs of things that are equivalent, then I want the sums of things, one from each pair, to be equivalent. So let's write it. Here is the theorem we will prove. Theorem. It says, did not wipe off that erasing stuff enough. Let's see. There we go. Okay. Suppose that A over B is similar to X over Y, and C over D is similar to W over Z. Okay. Then AD plus BC over BD is similar to XZ plus YW over YZ. Okay, so to show this, and just to give us some intuition, what this is telling us is, oh, back to the other board. I forgot to switch the camera. Okay. So what this is telling us, if I can find a marker now that works, since I kind of messed that one up by getting washer fluid on it. This one is not very good. I'll use a dark blue. That'll be fine. Okay, so look at these conditions here. What these are telling us is that if AB has the same equivalence class as xy, and CD has the same equivalence class as W over Z, then A over B plus X over Y has the same equivalence class as C over D plus W over Z. Does that make sense? This is exactly what we were talking about before. That is, that our choice of representative elements that we use, the choice of elements we use to represent each equivalence class is not important when defining the sum of equivalence classes. You could pick either one you want from both of them, and no matter how you add it, you'll get the same equivalence class. That is the sum of the things. While it maybe lands you at different places, all of those places it lands you belong to the same chunk. Cool? Cool. All right. So let's show this. Okay. Proof. Okay. By hypothesis, AY is equal to XB, and CZ is equal to WD. Right? That's what these two conditions up here tell us. Okay. We want to show that AD plus BC times YZ is equal to XZ plus YW times BD. Yeah? That is, you're going to show this thing and this thing are equivalent. Feeling good about that? Okay. So how are we going to do this? Well, we're going to use our hypothesis to take one side of this and turn it into the other. That is, we're going to use these two facts to take this side and, using only these facts and basic manipulations, turn it into that. So let's try it, okay? So we say, hey, AD plus BC times YZ. Well, would you agree that AD plus BC times YZ is AD times YZ plus BC times YZ? That is, we can do distributing. We can distribute multiplication across addition. Yeah? Okay. Now, we're going to do a little bit of reordering and go, all right, what do I know? I know AY is XB. I've got an A and I've got a Y. Let me just regroup my multiplication a little bit and go, hey, I've got AY and DZ. Now over here, I know that CZ is WD, so I'm going to get my C and Z together. CZ and BY. Do you agree with this so far? All I did was I reordered my multiplication. It doesn't matter what order you do multiplication in, so you can flop it all around all you want. Yeah? Okay. Now, by hypothesis, we say AY is XB, so this is XB times DZ plus WD times BY, since after all, CZ is WD. So this, just to be clear, we can justify every step if we want. This first one is by distributivity of multiplication over addition. This is by the commutativity of multiplication. That is, it doesn't matter what order you do it in. And then this here is by hypothesis. Now, in our next steps, we're basically going to go backwards. We're going to do some more commutativity. We'll do an undistributing step, and we'll produce the thing we want. So we want to get XZ plus YW times BD. All right. So wherever I've put my marker now, what did I just do with that thing? That's the purple one. Is it right here? Oh, yeah. No, that's a different color blue. Oh, what? Did anyone see where that marker went? Oh, no, here it is. For a second, I was like, that marker is fully vanished. That's weird. All right, so here, we want to get xz. So I'm going to get xz here, and bd, plus, now I want yw, and I'll again do bd. This is by, yet again, commutativity. Of multiplication. And now we say, okay, cool. Let's undistribute and get xz plus yw times bd. That is, let's factor out this bd. And so this is by distributivity. Of multiplication over addition. And now, look, I've produced what I want. So, AD plus BC over BD is similar to XZ plus YW over YZ whenever A over B is similar to X over Y and C over D is similar to W over Z. That is, we have shown our desired result. We have said, hey, this part right here, this just says A over B is similar to Y, or X over Y. And this here says C over D is similar to W over Z. And here, this thing that we want to show says exactly what we want here. That is, these things are the same, yeah? So we started out by supposing these things and getting this. Nice? Okay. So the answer is yes, we can indeed define an addition on the equivalence classes of fractions under this equivalence relation using any old representative element you want to add together two equivalence classes. All right. So the answer is yes. That's not so bad. Now, here's another fact. Here's a theorem that I won't prove since it basically follows the same kind of thing. We might be able to prove it. I don't know. We'll see if we have time. So suppose that A over B is similar to X over Y and C over D is similar to W over Z. Then the claim is that AC over BD is similar to XW over YZ. That is, we can also define multiplication of equivalence classes of fractions by just taking the multiplication of two equivalence classes to be the equivalence class of the multiplication of any two representative elements, one from each. Yeah? Kind of cool? Okay. If you wanted to prove this, what would you do? I'm seeing some looks of, I don't know about this. So let's just prove it. Let's try it. Proof. So suppose AY is equal to XB and CZ is equal to WD. That is, suppose our hypotheses. Okay. We want to show that ACYZ is equal to XWBD. This is hard to read probably for people looking at this online. Maybe I should use a darker marker if I can. Let's see if I have the ability to do. So we want ACYZ to be equal to XWBD. That is, we want our conclusion. How will we get there? What would you do? Oh, here's a brown marker. That'll probably work well. We'll take one side and we'll turn it into the other using our hypotheses. right? Okay, so we say, hey look, AC times YZ equals AY times CZ by commutativity. And now by our hypotheses, AY is XB and CZ is WD. And now I can just use commutativity yet again to get XW BD. Is this reasonable? I hope. Yeah? So this is commutativity. This is by hypothesis. And again, by the commutativity of multiplication. Yeah? Cool. Yes? Do you have a marker? Well, I will owe you a marker. I will bring you one next time. Or just steal one from one of the classrooms to get us back. But cool. Nice. Yeah, hopefully this works well. We'll see. Yeah, that's a really good one. Nice. Sweet. So, we have concluded now. So, I'll write it this way. If A over B has the same equivalence class as X over Y, and C over D has the same equivalence class as W over Z, then A over B times C over D has the same equivalence class as X over Y times W over Z. That is, we can define a multiplication on equivalence classes by just multiplying any two representative elements, one from each, and looking at its equivalence class. Nice? Nice. Very fun. So the rationals. Your sense that all fractions are not so different, that is, that you could talk about 1/2 the same as 1/4 and perform operations like that, is now hopefully more well justified to you, right? What you're really doing is you're doing arithmetic on equivalence classes, and you're showing what equivalence class you get by selecting representative elements. And you have total freedom in selecting representative elements, since the addition and multiplication of equivalence classes is a well-defined operation, as we've just shown. Nice? Super nice, right? Okay, well, this is a good place to lead into the next chunk of our class, which will be Chapter 5. We will revisit the rationals in great depth quite soon. But up next, we will talk about functions. We won't have a huge amount of time to do this right now, but I just kind of want to give you the picture of what this is all about. So you maybe have seen functions before, but my guess is you've seen them expressed in function notation and everything, right? People like to, we have such like an automatic familiarity with machines and devices, right? That I think are, the way functions tend to be presented to people has certainly come to reflect that. That is, like, it depends, the presentation relies a lot on people's familiarity with using machines and devices, in the sense that, you know, there are many different things. You put a quarter in a soda machine and you get out a soda. You don't put a quarter, you put in like $2.50 at this point, right? $3, and you get out a soda. Okay, cool. This kind of stuff. You put something in, you get something out. Function notation kind of reflects this, right? It's like a little device you use where you put a thing in it and a different thing pops out. There's a way easier way to look at functions that I think makes way more sense intuitively. And I don't want to say like the other way is bad. It's certainly perfectly reasonable, and we'll do this a whole lot. But in Chapter 5, when we talk about functions, I think it's way clearer to think about it like this. So here's the setup. If you have two sets of stuff, two big old blobs, A and B, you've got some stuff in each one. What functions are is arrows between blobs, if you want to think of it like this. So maybe you've got here, you've got A, B, and C. You've got 1, 2, and 3. You could have different numbers of elements, but functions are just arrows between blobs, if you want to think of it like that. And you say, hey, what does a function do? Well, it picks a thing to draw arrows from. So a function f sending A to B is just a thing where you put something in, you get something out. That's like the mechanistic interpretation. Or another way of thinking of it is that the arrow has a tail and like a head. Like it's got a pointy part and a part that's not pointy, right? It's got slots. It's got order to it. That is, you can think of a function as a particularly nice type of relation, as a collection of ordered pairs. Does that make some sense? So you could, in this case, represent this function by A2, B1, and C3. Yeah? Okay. This is not so different from what we just talked about with relations. Yeah? Functions are a nice type of relation. Just like an equivalence relation is a nice type of relation, functions are another nice type of relation. Specifically, to have a function, you can't have more than one arrow from anything on the left side. If you have something like this, then it says B gets sent to both 1 and 2. No good. Functions are the particular types of relations where everything on the left has but one arrow pointing out of it, and each thing on the left has one arrow pointing out of it. That is, if I added a D right here and did not have an arrow, I would no longer have a function. So the way we'll set up functions is we'll set them up as relations, that is, subsets of a product of two sets, with the nice condition that every element of the first set appears but once in the first entry of one of the elements of the relation. So maybe it sounds like a mouthful when you say it like that, but just capturing the idea here with arrows makes it relatively clear what's going on. So if I put like, D2 here, okay, cool. Everything over here has one arrow going out of it, and everything over there has no more than one arrow going out of it. No more than one, no less than one, right? Exactly one arrow going out of each thing. Ordered pairs, exactly every element of A is in the first entry. And none of them are repeated. Okay, we'll talk about this more next time. We'll think about the different types of functions you could have. It kind of immediately suggests itself. For instance, this is a kind of weird one in the sense that, hey, look, 2 gets hit twice. Maybe we want to categorize ones where things on the right only get hit once. Or maybe we want to categorize it so that you can say, well, I want everything on the right to get hit once, unlike what happens here. Yeah? This will lead to our idea of surjective and injective functions. And it'll all be easy because it's just arrows between blobs. So I'll see you next time. Have a great day.